Hello guys, welcome to another video from Computerscience channel. In this video, we're gonna solve the 8th problem from Sipser textbook, and actually this problem is about NFAs. And in this question specifically, we're gonna talk about the property of union. We know that the union of two regular languages is also a regular language. So in this question, we're gonna practice this issue together and learn something about this. And yes, that's it. Let's solve it together. Okay guys, as you can see here, actually exercise 1.8 says that use the construction given in the proof of theorem 1.45. So give the set diagram of NFAs recognizing the union of the languages described in actually part A and part B. So first of all, let's look at the proof here. The proof says that we have a regular languages A1 and A2, and we want to prove that the union of A1 and A2 is regular. Actually here, the basic idea is that we define a new starter state except our starter state in A1 and A2, and after that define epsilon arrow to a starter state of A1 and A2. So actually in new NFA, as you can see here in this part, we have one starter state and two epsilon arrow to a starter state of A1 and A2. And this is how we construct the NFA for union of two languages. So let's back to the question. Actually, part A says that we're gonna construct the NFA for union of languages that describe in exercise 1.6 part A and 1.6 part B. And as you can see here, we have the question 1.6. In part A, it says that actually we have W, that W begins with a 1 and ends with a 0. And in part B says that W contains at least 3 ones. So actually I write this part in my notebook here, and actually I call the first part L1 and the second part L2. Now let's construct an NFA, or better say actually DFA, because in part actually question 1.6 we must construct a DFA. So actually first let's construct the DFA for L1. For L1, as you can see here, we have two conditions. W must begins with a 1, and after that, it must ends with a 0. So first, we are in our start state. If we start with a 1, we are okay, but if we start with a 0, actually, we can never reach our accepted state. So after that, the transition doesn't matter for us, and we can never reach the accepted state. But if we start with a 1, after that, we must end with a 0. So after that, if we see a 0 anytime, we have a chance to end our string with a actually 0. And this is our accepted state. But in this part, if we see a 1, we back to this part. Because after that, if we see another 0, we have the chance to reach our accepted state again. So it will become like that. In our accepted state, if we see a 0, it doesn't matter, because anytime we see a 0, actually we end our string with a 0, so it's okay. And in actually last part, we must define a transition for 1. Actually, it will back to this part, because we know that if we see a 1, it doesn't matter for us. It will never reach the accepted state. We must see a 0 here. And yes, this is the DFA actually for L1. After that, for L2. For L2, actually, this is so simple. L2 says that W contains at least 3 ones. So the number of 0 doesn't matter for us. Actually, it don't matter for us. And we draw the transition for zeros like this. And anytime we see a 1, we will go to our next state like this and this and this until we reach 3 ones at least. So after that, actually here, after that, the number of ones don't matter for us because we reach our condition that says that W must contains at least 3 ones. So after that, it will become like this, and this is our accepted state. So this is the DFA for L2. Now let's construct the NFA for the union of L1 and L2. As you can sorry for this part. Actually, based on the theorem that you see, if we want to construct an NFA for union of two languages, so we said we want to construct an NFA for the union of L1 and L2. We must define a new start state, so it will become like this, and after that we define our epsilon arrows like this, and after that all we have to do, we just have to draw our DFAs again. So in our for part L1 it will become like this. Actually, we are in our start state in L1, and after that we must define our transition. So yes, it will become like this. This is our active state here, and like this is for L1, and for L2 actually it will become like this. The number of 0 doesn't matter for us, so all we have to do to draw the transition for ones, this is all matter. So it will become something like this. And yes, this is the NFA for union of L1 and L2 actually. And yes, this is okay. Actually, all we do in this part, we did in this part was that we define a new start state with new epsilon arrows, and after that we just somehow concat L1 and L2 to these parts. And yes, that's it. Now let's go for part B. Actually, I write part B here. It was the union of question 1.6 part C and part F. Part C, part C says that W contains the substring 0101, that we can assume that W is equal to x0101y for some x and y. And for part F says that W doesn't contain the substring 110. So actually, first let's actually construct the DFA for part C. Actually, so we call this part L1 actually. So this is L1 and this is L2. For L1, it says that W contains the substring 0101. So actually this part is a little tricky. It will become like this. In our start state, if we want to have this pattern, we must start with a 0. So here the transition for 1 doesn't matter for us, and we can't see a new state with this transition here. But if we see a 1, we have a chance that we can reach our pattern. So it will become like this. Actually, first of all, let's construct a full DFA just for pattern, no matter other transitions. So it will become something like this here. Yes. And this is our accepted state. Now let's construct and define our transition. In second state, actually, if we see a 0, we will stay there because we know that the string 00101 is in our language, so we will stay here. And after that, for third state, in this part, if we see a 1, we go back to our start state because we break our pattern and we must start again. So it will become like this. And for fourth state, if we see a 0, we go back to this part because actually if we see a 0, we can actually start our pattern again, and we use this new 0 to start our state. So based on that, we don't come back to our start state, we will back to our second state. So this is something like this. And for final state, after that we reach our pattern, and after that we can't see anything. Actually, this is part Y, so it don't matter for us. And yes, this is the DFA for L1. Now let's construct the DFA for L2. For L2, L2 says that W doesn't contain the substring 110. We know that the regular languages are closed under complements, so we can first assume that our language is that W contains the substring 110, and after that all we have to do replace our normal state with accepted state and our accepted state with normal state. So with this actually method, it will become so much simple, and it will become like something like this, actually, like this. First, let's construct the part that we can recognize our pattern, and this is something like this. We have transition for 1, and after that for another 1, and for another 0. We know that in first part, if we see a 0, it doesn't matter for us because we don't have our pattern, so we will stay there. But for second state, actually, yes, for second state, if we see a 0, we will back to our first state, so it will become like this. And for third state, if we see a 1, actually we are still in our pattern, so we will still stay there, and it will become like this. Actually, sorry, like this. And for our final state, after that we reach our pattern. It is something like part Y for last question, and enough. Actually, after that, other transition doesn't matter for us, so it will become like this. Actually, if the question says that W contains the substring 110, our accepted state was our final state here. But it says that W doesn't contain the substring 110. So all we have to do is that replace our normal state with accepted state and our accepted state with normal state. And it will become something like this. And yes, this is the DFA for L2. Now let's construct the NFA for union of L1 and L2. And it will become actually something like this. For union of L1 and L2, we define a new start state with epsilon transitions, actually like this for this part. And after that, all we have to do is that somehow concat our DFAs for L1 and L2 to this part. So first, let's start with L1. Actually, we have the DFA for L1 in this part, so all we have to do is that draw this again. This is our start state in L1, and we will repeat our transition. This is for 0 and 1 here. This is another transition for 1 here, and after that for 0 here. And with this transition, we will back to this with 0, and finally with another 1. And yes, this is our accepted state. And yes, so this is for part L1. for part L2, actually let's draw it. It will become like this. This is transition for one, and after that for another one, and after that for another 0. So, and yes, like this is for 1, and this is for 0, and another transition for 0 here. And actually let me fix this part. Yes, and yes, that's it. This is the NFA that we construct for union of L1 and L2 in part B, and that's it. That was the solution for question 8th question in Sipser textbook. I hope you guys enjoyed this video and learned some useful things from this video. Actually, the Sipser textbook is so useful. You can learn a lot of things from this book, and yes, all you have to do is that practice this book again and again, and learn a lot of things about computational theory. And that's it. And if you can't subscribe to my channel, this is a big motive for me, to I continue to actually make some videos about a solution, and maybe later for another topics. And if you have any comments, leave it in comment part. I will read all of them. And yes, that's it. I hope you guys have a nice day, and goodbye.